Hello, I can relax a little more on this one. I got a little more time, a little less information. I thought about coming in on stilts so I could better approximate my colleague, Chris Smemoe, but figured I'd probably trip on my feet if I did that. So today we're talking about web services resources for hydrologic and hydraulic modeling. And so this is our itinerary. Going to talk about what hydrologic modeling is, hydraulic modeling, web services, using web services for hydrologic and hydraulic models, and then we're going to take a look at a case study for web services for a fast floodplain analysis. Hydrologic modeling is simply determine the water quantity and or water quality information at one or more points in a watershed. The basic information required to create a hydrologic model is having the watershed elevations, determining the soil properties and or land use information, getting your rainfall and climate information, and then determining your watershed initial conditions. At that point, you can determine your water surface elevations and velocities at one or more points. On the hydraulic modeling, the purpose is to determine water surface elevations and velocities at one or more points on a river. To do hydraulic modeling data, this is what you're going to need river and floodplain elevations, which is bathymetry, your riverbank and thalweg lines, and a river and floodplain roughness properties. And those can come from land use and soil types. And so what are web services? They're GIS websites that have capability of instantly trimming and transmitting raster or vector GIS data to a user's computer. In other words, you get on your computer, pull the information, and just the information you need in that area. So there are several types of web services. One is the Web Map Service, or WMS, not to be confused with the Watershed Modeling System, Web Map Service, Web Feature Service, and Tile Services, and then the Representational State Transfer Services. So Web Map Service are those that give us an image of a desired area. So, these are your aerial photographs, your topo maps, street maps, similar to, say, Google Maps. Web Feature Services are ones that give us specific vector information for a desired area. So you'll have floodplain boundary polygons, land use polygons, and property boundary information. Whereas this one is more of an image. This one gives you lines and information and areas and what we call vectors in programming. And then you have tile services, and these give us tiles with some kind of raster information on it. This can be a given latitude, longitude, and zoom level. So one example of this is elevation data. So you'll get a tile or a grid, and you'll know the elevation across that area. And then REST services. These are services that are useful for downloading many types of raster and vector data, especially useful for gathering historical climate data, and that has a time series attached to it, from the National Oceanic and Atmospheric Administration, or NOAA. And then web services and hydrologic modeling, government or other publicly available website services are available for these following modeling data: watershed elevations, which is a tile service, aerial photographs and topographic maps. Again, these are optional, but very nice to have. Make your project pop a little better, help you find where you need to perform your arcs and your modeling. And that's a web map service. Soil properties and land use information, which is a web map service. And then the rainfall and climate information, which is an REST service. As an example of doing a web service example for hydrology, this is a little place over by Provo called Rock Canyon. He's delineated a watershed, given us a curve number. And we're going to watch a quick little video on web services. Now we'll see if this pops up on both screens or just mine. Yeah, just mine.
This video shows.
Give me just a second here. At least you guys can't see me scrolling through everything. Duplicate. Keep change. Okay, now we're good.
Shows how simple it is to use WMS to gather data and create an HMS model of a watershed near Park City, Utah. We will use the WMS Hydrologic Modeling Wizard to download data and to automatically build an HMS model. After the model is built using WMS, we will export it to an HMS file and run the model in the HMS interface. The first step in defining an HMS model is to define your project file name. After you have defined a project file name, you can define a coordinate projection to use in your project and then define the boundary of your model area. For this project, we will use the UTM projection with metric units. You can use the Virtual Earth Map Locator window to locate and then define your project boundary. For this simulation, we will select a watershed in Park City, Utah as the project area. Using WMS, you can download all the necessary data to delineate your watershed and compute hydrologic and geometric parameters from online data sources. There are tools to download elevation data, land cover data, aerial photographs, maps, and other images, vector-based land use and soil data, and other data that is useful in watershed modeling. WMS downloads, imports, and displays all the selected data for the model area you select. WMS uses a model called Topaz to compute the flow patterns in your watershed. This model is used to determine high flow accumulation areas where streams may form. After you have computed the flow accumulation locations using Topaz, select one or more outlet locations for your watershed model. In this model, we will define an outlet near a bridge passing over one of the streams. By doing this, we can use HMS to compute the hydrograph under this bridge during a large storm. After defining the outlet point, delineate the watershed by clicking on the Delineate Watershed button. When delineating the watershed, WMS computes all the geometric parameters necessary for running your HMS model. Select HEC HMS as the desired model and initialize the model data. Define a start and end time for your model simulation. This model will run for 2 days with a 10-minute time increment. WMS downloaded a land use grid and soil polygons. This spatial data will be used to compute a composite curve number for the watershed. Before computing the curve number, we must first join tables containing soil-specific information with each of the polygons in the soil layers and convert the polygons intersecting the watershed to WMS polygons in a soil type coverage that can be used for computing the curve number. You can compute the curve number and other hydrologic parameters using the Compute GIS Attributes dialog. This dialog combines the information in the soil type coverage and the land use grid to determine an area averaged curve number value for your watershed. Comma-delimited tables are available for download from Aquaveo's help pages that relate land use IDs to curve number values for various soil types. After the composite curve number is computed, WMS displays a report file that shows the various land use and soil combinations in your watershed with the details of the curve number computation. Another important hydrologic parameter computed by WMS is the time of concentration, or the lag time. You can select from WMS' extensive library of equations, or you can define your own equation for computing the necessary time parameters for hydrologic modeling in your watershed. We will select the SCS method for computing the lag time in this model. After you have defined your watershed curve number and lag time, you can finish setting up your HMS model by defining the SCS curve number loss method and the SCS transform for your HMS model. We will build our model using an SCS Type 2 100-year 24-hour storm. The standard design curve associated with this storm is included with WMS. You can use NOAA Atlas 14 to get the 100-year 24-hour precipitation value of 3.13 inches for this watershed in Park City, Utah. Fill in the precipitation depth in the HMS meteorological model window. The Cleanup Model button runs some common tasks that are often performed to clean up your display and check your model before running it. The model is cleaned up and no errors are detected in the HMS model. After completing the hydrologic model, you can save your HMS model and import your model into the HMS interface. Once you have imported your model into HMS, you can view or edit your model data and compute the results from your WMS model. HMS has a rich set of tools for viewing the hydrograph and other output from your hydrologic model.
Okay, so that showed us an example of going through the hydraulic tool of going through WMS to using web services to be able to, I want to restart this one over again. But it shows us how we can go just using the web services that are available, download all the information we need to do a hydrologic model. And I am not sure how to change this from, no, never mind. Let's see. Okay, there we go. So we were able to download all the information we needed, build a model, make our own changes, save it all there as a project so we can come back and get right back into it. And we didn't have to go out into the field and do any measurements or have too much work to even get the data. A lot of times it's just, let me just drag a box across my interface, download the information, the aerial maps. In this case, it was showing the wizard, which you just check the boxes you want, get the data, and it pulls it up for you. Now, the web services and hydraulic modeling, you're going to use the following data: floodplain and some bathymetry elevations, which is a tile service; riverbank and thalweg lines, which is a web feature service; aerial photographs and topographic maps, again optional, web map service; and then the river and floodplain roughness properties, which is a web map service as well. One of our latest tools is here for the fast floodplain analysis. And this tool uses a vertical offset to automatically offset the 100-year FEMA floodplain maps to analyze extreme flood scenarios. So this will download the data for the FEMA 100-year plain water surface elevations, floodplain ground elevations, and a FEMA flood map and an aerial photograph. So here's an example of this being performed. And my colleague just pulls this right off of the web services, drag a line, and it pulls in the red value, which is the 100-year floodplain, and then he added a 5-foot vertical offset and gave us a 100-year floodplain with a little bit of a freeboard, 5-foot vertical offset on it. So to summarize, we've defined what hydrologic modeling is, hydraulic modeling. We've defined the different web services. And then we've shown what you can use the web services for hydrologic and hydraulic models, what web services you would need. We showed you a case study for determining that in fast floodplain analysis. Do we have any questions? Oh.
So web services, is that different from actually downloading like a TIFF or a TIFF or something like that?
Oftentimes it will be downloading geotiffs. There are a couple ways it can be done. It can just pull off a static image that you save. It can also be just a background so that you can pan around and move, and it just continually updates and gives you an image. And depending on how far in and out you zoom, it will change that image. And it doesn't save with your project, but then whenever you get online and you pull it back up and go online, it'll pull up that same web service and that same background image. In that way, it acts a lot like Google Earth.
Any other questions?
Okay, if you have any others, I'm just over in the booth over there. Come by and see us.